So we'd go through and summarize. If you're going to go through and do all the writing that I would ask you to do, we'd convert all our known information across, put down our initial values, our temperatures, volume, Kc. Okay. One of the things that we might note right away is what's the size of our equilibrium constant? Big or really small? Relatively big, or ultimately not really small, which means we already know by looking at this problem that it's going to be a long solve. Okay? So the other thing that's kind of nice here, we want to go through and solve for what we can easily calculate. One thing you might notice is that we gave you a nice volume value. With 1 liter, we don't really have to do a calculation. We just do the unit conversion, and we now have our concentration for each of those species. We can move to our ice chart. We set up our equation. Is that the equation? Yeah, okay. For some reason it just looked weird. We'll plug in the information that we do know. We know our initials all the way across. We weren't given any carbon dioxide or hydrogen to start with, so we assume those are 0. We can now go through and determine our changes. Oh, shoot. I don't want to goof and make sure I run off of the slides. What did I decide was X later on? Oh, they're all 1-to-1, so that's not going to be a big deal. That was a dumb question. Since it's all 1-to-1, we aren't too concerned about what we set up X to be. Okay, so we can pick any one of these. Actually, sorry, before we do that, first thing that we'll do, calculate Q to determine how it compares to our equilibrium constant. Our Q value is 0, which means our products must form, so those are going to be positives. Our change for our starting materials will be negative. Yes?
On the exam, it seems like pretty much every problem we solve, one of those is going to be 0. Well, the last 3 that we solved. So
possibly.
Is that what we should?
You shouldn't assume that, okay? Because it's not always going to be the case. In most circumstances, it is. Okay? But you might very well see a problem where it's not, which means you have to go through and solve to determine if you're at equilibrium or not and which way the equilibrium is going to shift. Okay? So you do have to account for that. You can't just ignore it. Okay? What do we want to decide X is equal to? With this problem, because our coefficients in our balanced equation are all 1, does it matter? No, we can just plug in X all the way through. Okay. Our equilibrium concentrations, our initial plus our change. So it's 1 plus a negative X, which is 1 minus X, 2 minus X, X, and X. Can we solve directly for X? Nope. So here's where we would move into our pink color. If I was paying any attention, since I'm kind of paying attention, we'll do it. We would say K is equal to, 4. That's why you guys telling me that. Our number was 4. We know that's the concentration of our products times the concentration of our concentration of our products over the concentration of our reactants. Is it H2O? We could then go through, substitute in our equilibrium concentrations that we found from our ice chart. Okay, and we could then try and decide and evaluate if that works or not. So let's go ahead and have it actually typed up for us. Yes?
How did you have the 4 again?
K equals 4 is given. It's one of the very first things at the beginning. Yeah. Which is one of the reasons why I would recommend that you write it down. So if you spend the time to convert the question across into those extra little numbers, hopefully you'll see it. It'll be a little bit easier. You'll remember a little bit better. Okay? We could go through and attempt to solve this or simplify. I didn't even simplify yet. We'll just assume X is less than 1. Why do we always want to assume? How much easier is it going to be to solve an assumption versus not solve the assumption? It's usually a lot easier to solve our assumption. It's something that you can almost do just on the calculator. So if you make the assumption, you can almost solve your answer in a matter of seconds. If you don't make the assumption, it takes you 2 to 3 minutes probably, okay, with all the algebraic manipulations you'd have to do thereafter. So I would first assume, I would do some of that math in my head, and I would go through, punch it into the calculator, and what do I get for x? X would equal 2.8. Okay? Once we've got an x value, what do we need to do? We could substitute in, okay, but before I even spend the time to do that, I want to verify that my assumption is valid. The assumption that I made was that x is much smaller than 1. What did I say x was? 2.8. Is 2.8 much smaller than 1? No, which means the assumption is invalid, and we must solve this the long way. Which means we have to go back to our full equilibrium expression. So this guy up here, rearrange and solve a quadratic equation. In the worst case, in some cases, you can do some other simplifications and solve for x. Okay? Everybody remembers how to solve a quadratic, right? Is there a question there? Okay, sorry. So we go through, you can see all the fun kind of algebraic flips and swaps. And assuming I did all the algebra correctly, you end up with that expression. Okay? That expression we would then need to solve for x. How do you do that? That's your quadratic formula. Okay? X would be equal to this big old beastly equation. What are the B's, A's, and C's? It's the numbers in front of our equation. So what we're looking at is this one is A, B, and C. What is the value for B? Just want to make sure you're including it. It's negative 12. Include the sign in front of your number. A would be 3, C would be 8. Okay? So we could go through, plug our numbers into that equation. Oh, I actually wrote it there. That was nice of me. Go through all of that manipulation. Yes, I would highly recommend, at least at this stage, that you go through and substitute all of those numbers in, including their signs, and simplify kind of stepwise until you get down to a pseudo-final expression. And we'd end up, again, with 2 numbers. Okay, anytime you take, or we've got that plus minus already incorporated in there, we'll get 2 values for x. These would be our 2 numbers. Of these 2, which one is valid? Only the smallest one. Why? If we go back to our equation, we had one of our equilibrium concentrations, I believe, was 1 minus x. If x was 3.15, does that give you a value that works or makes sense? No. So it can't be the 3.15. Our answer is the 0.845. Yes. Not yet, sorry.
Where did when you plugged in the ABC, where
Yes.
did the 3 come from?
The 3 for A.
Yeah.
When you go through and solve this equation, the first thing I did was take 4 times the multiplication of these 2. And you end up with this expression. Now we group all the terms together. If I bring x squared over, I get my 3x squared. Yes?
Is that how you got your assumption that x was a lot smaller?
No. So the assumption of why x was smaller is we looked at our equilibrium expression, which we do have way up at the top. To do our assumption, what we have to look at is where x shows up in an addition-subtraction type equation. So it has nothing to do with what x actually is. It has everything to do with that equation there. Okay, so to do an assumption, I would say for this one to be valid, I guess we can do colors here. I would say x must be less than, much less than 1. Okay? In the other case, officially we have two assumptions. We assume over here that x is much less than 2. Okay. When we go through and solve, we do verify that x is not much less. Okay. But the assumption won't give us that value. We have to go through and do the long solve. Okay. Just because I know there's some smarter person, to put it, I guess, politely, has gone through calculus or algebra with their big fancy graphing calculators and is going, ha ha ha, I have this little sneak, I don't have to do all this. That's true. If you have a graphing calculator, the graphing calculators usually have a quadratic solve buried somewhere within the functions. Do not ask me how to do that. I have no idea. Okay? So does anybody know how to get your calculator to do the quadratic solve? Really? Nobody? Oh, you had to write your own program. Okay. I thought it was already in there.
I've taken through Calc 3, but we never used the quadratic formula hardly. Like if we did, we just did it.
So for anybody that knows how to get it programmed in, if you could write up a protocol on how to get it programmed in, I'm more than willing to share that, put that up on Canvas so that you guys all have access to it. It's only going to be one problem. I won't make you do this more than once, okay, on the exam. And it would just be this first exam. So, and it would most definitely show up in which part of the exam? The show your work part. Okay? So the multiple choice answer itself would be relatively worthless as far as points. What I'd be looking for is all of the work. Okay? And as far as all of the work goes, if you have a quadratic solver on your calculator, I'm fine with you getting up to this point and saying use calculator for quadratic solve. Okay? I'm fine with that. Yes?
I think if you have a TIE 6 anyway for the second
If-
PRTN, it's
I'm-
a poly, so you can put your orders in the second order.
We'll go through and figure that out either in lab when I have somebody's calculator to play with in lab. Otherwise, keep your eye on Canvas. If someone figures it out, you can always post a discussion announcement explaining exactly how to do it. I don't want to spend any time on it right now, or any more time on it.
Would this be considered a problem?
Yeah.
Or would it not be?
Yeah, this would be kind of an A-level problem because it involves lots of mathematics and trying to push all the way through. Okay? Again, we'd go back to what we'd initially set. The question asks, what are the equilibrium concentrations of all species? You'd plug your x value back into your equilibrium. Did I not put that on there? Oh. Plug our x value in, and we'd get our equilibrium concentrations. Okay? With the questions that we just walked through here, I showed you how to solve for all of them. On an exam, what are the odds I'd ask you to solve for all of them? In a single multiple choice exam or question, that's not going to be particularly easy to do. Okay? So I would ask for 1. That is why it is incredibly important to make sure you answer the question asked. Know what the x value is. Make sure that when you answer the question, you're answering it for that specific species. Okay? The question that was asked. Make sense? Okay. Pretty sure that's it with those solves. Any questions on ice charts? Okay. As much fun as these are, you would hope that we wouldn't have to deal with them ever again in the rest of the semester. They're only going to get more complicated. Okay? So practice them. You will see ice charts show up for the next 2 chapters. Okay? And they will show up on your final. They are incredibly important. If you have to take more chemistry up through biochemistry brings them back. Okay? With a vengeance. Okay? So please spend the time to get them figured out now. It'll make the rest of the semester a little bit easier.
I wasn't here yesterday. What is Q?
Q is the reaction coefficient. What you're looking at there is it's the same solve as K, except that you're not at equilibrium. So it allows you to determine how your equilibrium shifts. Okay. The rest of these, like I said before, can be kind of pseudo-derived. So we're looking at, I think, 3 more equilibria type rules. I don't think we'll see them beyond this exam. I can't remember if we see them beyond this exam at least. Okay? So, adding equations. When we looked at mechanisms, we had multiple equations. We could add those up to get our overall reaction. When we tried to determine the overall rate, what did we have to do? We had to evaluate which was the slow step, all that fun jazz, and go through, do all our stupid solves and all that fun stuff. Okay, so a big god-awful mess. When it comes to equilibria, what's happening when we go through and do that same idea with an equilibrium reaction? Okay, what's the equilibrium constant for our first step equal to? Don't all tell me at once. How do you solve for equilibrium constant? Try that simpler question. Products over reactants. You're not answering right because you're just tired of answering that same question? Is that a yes? Yeah, okay. I'll accept that. Products over our reactants. We could go through and do that for our other K. For K is step 2. What do we get? NOBR squared over, whoops, yeah, that's right. 2 times concentration of NO, right? So go through all that work. Okay, what's the overall equilibrium constant? Could look at K overall, go through and solve that. Sorry, I got to look at it. Write this out a whole bunch. Actually, I'm going to lie because I wrote it. Okay? We look at our K overall and we get that expression. What's the relationship between our K overall and the Ks of our previous steps? Does anybody see that? NOBR squared is in the numerator in our K overall. So if we're going to try and figure out how we can get these to equal this, I should probably get this set up in the numerator. So we're trying to determine how we can get our K overall. Whoops, well, there we go. Never mind. Too late. This was K2. NOBR squared in our numerator. Okay, we wanted NO, and then trying to figure out what to do with K1. Okay, we just have to kind of align this up as best we can. You notice K overall does not have NOBR2 in it. And when we look at K2, that species shows up in our numerator. So what we've got to do with our next multiplication is somehow align K1 such that that species cancels out as far as units. So what do? Go back to K1 and see where NOBR2 shows up. Where does it show up? In the numerator. So what do I need to do to get those two terms to cancel each other? Multiply. What do I end up finding out? K overall is equal to the equilibrium constants for the individual reactions above multiplied by each other. Okay? This can be helpful if we're given numbers. So if I know the equilibrium constant for step 1 was, say, 2.4, I could then, and equilibrium constant for K2 was, say, 3.2, K overall would be the multiplication of those two. So if for some reason I didn't or couldn't determine the actual concentrations in K overall to get an equilibrium constant, but I could do it of other reactions, I can add them up to, or add the reaction equations and multiply my equilibrium constants to give me an equilibrium constant for my overall reaction. Okay? What happens if we added two of the exact same equation to each other? What happens to the coefficients on everything in that equation? I don't think I can do this easily with this, but let's see. Nope, I can't. Let's say we ignore, we say it's not step 2, we say I just do the exact same equation. What happens in my balanced equation? Or my overall equation? What would happen? everything just doubles, which means the coefficients and our superscripts end up becoming 2 all the way through, right? So our k overall for doubling that would just be 2, which is what we said initially. If we change the coefficients in our equation, we have to change the exponents. What are we doing by doubling the coefficients? We're adding 2 of the exact same reaction, which is ultimately k, the equilibrium constant of one of those reactions, times the equilibrium constant of the other. So it's the same thing that we've already addressed. This just happens to be kind of the pseudo derivation of it. Hand.
Is that supposed to be BR2 on the K overall at the bottom?
Oh, yes. There should be a 2 there. Good eyes. Okay, yes.
Are you showing that the K overall was derived from
K overall, so what we tried to do was just look at the kind of symbol, I can't come up with a good word for it, the symbolic notation. And what we've derived is another expression. This other expression is that K overall is equal to the equilibrium constants of the reactions that you added multiplied by each other. Okay? So it's a longer derivation of just a simple rule, or simple rule. Very rarely used, but it does show up every so often. Okay? We can look again at perspective. Everybody loved perspective when we looked at rates. Remember all the negatives and positives? If we looked at the forward equilibrium, nitrogen oxide plus bromine goes to NOBr2 versus the reverse. NOBr2 goes to nitrogen oxide plus bromine. What is the relationship between those equilibrium constants? Kind of. What's the equilibrium constant equal to in each case? Please say it's there. Oh. Okay. I threw in some numbers on this one. K forward is the concentration of our products, NOBr2 over our reactants. K reverse, nitrogen oxide, our products, again, over our reactants. Okay. And we look at the numbers aren't positive and negative. Okay? And if it was negative, would that be a problem? Can we get a negative K value? No. So what is the relationship between these two? It's not just plus and minus, it's the inverse. Okay? So what we can do is punch into a calculator. We say 1 over 2.12 equals 4.72. They're related by the inverse. Okay? So if you know the equilibrium constant for the forward reaction, you also know the equilibrium constant for the reverse through that reversal or that inverse relationship. Okay? So that shows a couple different notations you could see for that. When it comes to catalysts, catalysts do end up changing the rate. Do they change the equilibrium constant? Okay, catalysts change the rate by doing what? Lowering the activation barrier, which ultimately does what to the rate? Speeds it. So the reaction goes faster. Okay? If we lower the activation barrier for the forward reaction, let's see if we can draw this on here. Say we've got a reaction, right? If we lower that activation barrier, our reaction forward goes faster, right? What about the reaction reverse? Same deal. It also goes faster. Okay? So when we're looking at a catalyst, it does change the rate. Okay? But when we look at equilibrium, we don't care about how long it takes to get to an individual species. All we care is that we're at equilibrium. Catalysts do not affect your equilibrium constant. All they do is allow you to get to equilibrium faster. Okay? So that's a pretty big difference between the rates or your kinetics and thermodynamics. Or let's do rates and equilibria. Okay? Rates deal with time, your activation barrier. Equilibria deals with just ultimately the energy difference between your reactants and products, just at the bottom half. There's no implication about rates or times. Okay? Anybody have it printed out? Was that the last slide? Okay. So that is the end of it. Hey, look at that, 2 minutes early. Any questions?
Going back to step 1 and 2, how do you tell which one's faster or slow?
As far as equilibria goes,
Yeah, the mechanism equations, how do you find out which one?
okay. So, yeah, so slow, fast with equilibria. Do we care which of these steps is slow or fast when we look at an equilibrium?
No.
No. Equilibria is irrelevant to time. So if you're asking about kinetics, how do we decide which one's slow or fast? There's 2 ways to approach that. The first way, I tell you. Nice and simple. The other way is you're given the rate expression, which is ultimately another way of telling you. You then get to go to those 2 equations and say, okay, let's assume the first one is slow. What would the rate be? Does it match what's given? If yes, which step is the slow one? First one. If no, which step is the slow one? The second one. It has to match what your overall rate is. Yep.